Hello. In this video, I'm going to show how the same set of Eurorack modules can be patched differently in order to create every type of analog synthesis available. We'll be trying West Coast, Non, and Thru-Zero FM, Yamaha DX7 style phase modulation, AM, amplitude modulation, ring modulation, wave shaping, and finally, additive and good old East Coast subtractive. Let me know if I missed one. What I want the moral of this video to be is that the essence of a modular is not always about buying one clever thing which just does one brilliant thing. It's about having a well-chosen selection of building blocks that, armed with the correct knowledge, you can patch to create the functionality you would get from complex modules. Now, to do it, I have a bunch of modules from a company called Shakmat. This is a range of analog modules, but with some clever digital control, and Shakmat are sponsoring this tutorial because they're cool like that. I want to stress that most of the things, perhaps with the exception of some phase modulation, really can apply to so many other modules as well. So if you have all of these, or some of these, or none of these, I hope you'll follow along. So what do we need? Well, first, two oscillators. I've got the Shakmat Banshee Reach, which is a very, very clever VCO because the Banshee Reach has phase modulation inputs, which isn't something I have seen really on any other analog oscillator. I'm sure there may be some that have it, but generally what you'd be looking for are FM inputs, which most oscillators have. That's separate to voltage per octave inputs. Now, ideally, the magic word you're looking for on your spec sheet is Thru-Zero FM. These ones are Thru-Zero. But you can also have a lot of fun if you have just plain FM inputs. To do AM synthesis, we're going to want a VCA, which we have within the jeweler's cast. To do ring modulation, you are going to want a ring modulator, which we have within the jeweler's cast. To do wave shaping, we're going to want a wave folder, which we have within the jeweler's cast. To blend oscillators together, we're also going to want a mixer, which we have within the jeweler's cast. It does that as well. And I would also say it's really nice to have a crossfader, which we have within the jeweler's cast. All right, jeweler's cast, steady on, mate. To do some subtractive, you're going to probably want a filter. And we have the Centaur's Gates. I love the names of these modules. They sound like things from The Legend of Zelda. This is a dual filter with multiple modes and a low-pass gate emulation. But yeah, a dual filter. Nice to have, isn't it? And then finally, some LFOs and envelopes. And I have the venerable maths, the yin and yang combination in black and silver. And really, this whole center section with two maths and this little Shakmat block, well, that is a very well specified analog synthesizer, if ever I saw one. You might want more VCAs to create more dynamic modulation over time. You might also want sequencers and other things. But what we're going to look at today is really a very, very broadly capable little synth. So let's try our first synthesis method. First up, we're going to explore FM synthesis in its various forms. And this may be the longest section of this video because it's the most nuanced and sort of interesting to get your head round. There's multiple different types of FM. And I really have to say that I think a lot of explanations on the internet leave something to be desired in terms of how they go about distilling the differences. There's often a lot of maths involved, and I don't know if you're like me, but that really does not work for me. I am very bad with mathematics. I blame a very mean maths teacher I had when I was a kid, and she put me off for life, quite frankly. So I will try and make this as practical as I can, whilst also explaining what it means when something is Thru-Zero, or how does phase modulation differ from FM. Spoiler alert, in practical terms, maybe not much, but there are differences. So let's explore them. Firstly, exponential FM. So what I've just done is I've turned up the resonance of a filter. And when you turn up a resonance of a filter that is capable of self-oscillation, it makes an almost perfect sine wave. Nothing's perfect in life, but it's good enough for our purposes. And if I do that on the other side as well, I get 2 sine waves. And we perhaps know that the width of waveforms corresponds to their pitch. If you turn them up, everything squeezes together. And if you widen them apart, everything becomes very deep and bassy. And all frequency modulation is asking something to change the speed of an oscillator, but to do so over a very short period. When this is down, the other oscillator is going to go slow. And when this is up, the other oscillator is going to go fast. It's really that simple. So if I copy the output of one and feed it into the frequency of the other, then we get this insane sound, which sounds like this. That's a very cool noise. It justifies my purchase of a modular synthesizer. And you can see that this sine wave speeds up in the bits where this one is high. It's squidging the little waveforms together at that point, and it slows right down in the bits where it is low. More on that in a sec. But the real fun of FM becomes in dynamically changing how much one thing modulates the frequency of another thing. And so if I was to go into an attenuator, what I've got is a volume control to choose how much one is going into the other. And I can do that with the jeweler's cast, comme ça. And then if I turn this dial, I dial in that effect. And what we might like to do is take an envelope and get that envelope to control this effect. What I'm doing here in effect is using a VCA to control how much that oscillator modulates the frequency of another. It's a cool effect, but here's an intrinsic thing that you may notice. The pitch changes with this sweep. Whoa! So if I was trying to make a melody using this technique, and I was trying to get movement in how I was sending one to the other, I couldn't really do it, but that doesn't stop me getting cool sounds. And you could be using LFOs to do that modulation. You could be using step sequencers to do that modulation between the oscillators. It's cool, and it's really whacked out and weird, but it's very hard to tune. In fact, every time you change the amount you are sending the oscillators to each other, you basically need to retune if your track is tuned to any particular scale, that is. What you can then do is move the pitch of both of the oscillators at the same time, and it will then stay in tune. But if you change the amount that they are modulating each other, then suddenly you'll have to retune. So it's quite tricky to use, but it's very whacked out. So Exponential is good for strange, blah kind of sounds, percussive, weird noises. It can be used for pitched stuff, but you can't dynamically change how the oscillators are modulating each other and still have it stay in tune. You have to fix it and then retune the oscillators accordingly. And every time you change the tuning, you'll also change the sound as well. And every time you change the sound, by changing this or the amount, you'll have to retune as well. Wouldn't it be good if there was a more forgiving way? Oh well, there is. So the next way, which is supported by the Banshee Reach and other oscillators, is called linear FM. And I do not wish to use mathematics to describe this, so I will simply say that linear FM uses a curve, or in fact a straight line, that means that it's much easier to tune. In fact, we should be able to dynamically change how the oscillators are affecting each other without changing the pitch. But we can only do this to a point. Linear FM does not let you do the whacked out things that you can do with Exponential, but you get more tuneful results from what it can do. So at the moment, we're hearing this Banshee Reach, which I'm going to call the carrier. And I'm calling it that because it carries sound into my ears. And the other Banshee Reach, I'm going to call the modulator because it modulates the carrier that carries sound into my ears. We don't actually hear the modulator, we just use it to affect the carrier. The modulator right now is a square wave, and the carrier is a sine wave. And if I go from the square wave output into the FM Thru-Zero inputs, then we get a cool tone. And if I change the modulator, the tone changes. And if I change the carrier, the pitch and tone change. You can actually see how the modulator is affecting the carrier. When it's high on the waveform, it's making it go a bit faster and squeezing together the sine wave just in that space. And when it's low, it's stretching out the sine wave in just that space, like it's a slinky. And this just creates a whole new waveform. If we turn this off, we can look at it. It's just this amazing, cool thing with sound waves going in every direction. And if we try a different waveform here, such as saw, we'll get different sounds and effects. Very cool. But this is principally quite similar to what we were doing with Exponential. But things just sound a bit less whacked out, don't they? We weren't getting those really high, mad sounds. Well, that's true. The other thing that's true will be what happens when we dynamically get one oscillator to affect the other. So if I disconnect the modulator from the carrier and instead run it through the jeweler's cast, then I can choose how much it goes into here. And then what I might like to do is take the output of a keyboard, in this instance a key steps 1 volt per octave output, and then I will copy it to both oscillators. So what's going to happen is they're both going to move with the voltage from the keyboard. That's the carrier with no modulation. And now let's send some of this other Banshee Reach in. Oh! Very cool. And remember, we had a little envelope, didn't we? Let's use that again. And let's let the envelope control the amount of sending knob. So what we're able to do here is dynamically change how one modulates the other and have it hold its tune. It's not as whacked out as Exponential FM, but it is easier to make melodies with. But what it does make a difference is the tuning ratios between the oscillators. And all I will say, some of them sound inharmonic, But you can sort of experiment and move the modulator until it sounds harmonious and in tune with the rest of your musical components. Another thing you can do is take the square wave output of the modulator and feed it into the sync input of the carrier, which will help lock the two together. Makes like quite whacked out sounds as well, where the sync point kind of creates an odd click. Linear is basically a more well-behaved version of exponential, where you don't get as extreme results. However, if you over-modulate a linear oscillator, you will find it goes out of tune. You might ask, why does it go out of tune? And the answer is that, remember before where we were seeing a waveform and we were seeing it was high when this is up and it goes low when this is down? If you have the oscillator a bit down low and you send a big positive and negative signal into its FM input, then all you're really doing is asking it to go super high for a split second and super low for a split second. And that lowness is so low that in fact the oscillator stops. And that is what Thru-Zero fixes, because the zero refers to 0 hertz. And if you ask an oscillator that is not Thru-Zero to go through zero, then it can't. It just stops. And that makes it go out of tune, because for a split second, it's really high. And it needs to be low for the equal amount of time for the pitch to kind of average out. And it isn't actually making a pitch if you're slamming it to 0. So that doesn't work, and it doesn't make the correct pitch. And so what a Thru-Zero oscillator like the Banshee Reach is doing is actually bending round and making a tone when it's asked to go slower than 0 hertz. It's like a kind of wave foldery trick. And all you need to know is it's actually able to bounce back from 0 and actually make some sound in these troughs. And that's what Thru-Zero means. And what's phase modulation, you ask? I'm so glad you asked. Although, let me tell you, this has taken me a long time to work out. That's FM. And that's phase modulation. Sounds really similar. And in some instances, it really can end up with the same effect. I heard a brilliant analogy for what phase modulation is versus FM. And that analogy is that FM is like you have a singer. And that singer is varying the pitch of their voice to create vibrato. That's FM. Phase modulation is asking the singer to sing at a constant pitch, but you're moving them backwards and forwards, away from you and towards you, really quickly, so that you get kind of a And the reason you get a change in pitch is, as you know, when an ambulance goes past you, you hear the Doppler effect. It sounds like the siren is rising when it's coming towards you, and that's because the sound waves are being squished together as they approach you. But as it goes away from you, the sound waves spread out, and it sounds lower in pitch. That's phase modulation in action. So actually, it's the equivalent of an ambulance going past versus the ambulance staying next to you and someone putting an LFO on the frequency modulation, which is to say, quite a similar effect, but it does have a tonal difference. And phase modulation is a bit better behaved. And in the instance of the Banshee Reach, there's a really nice thing, which is there's an amount control for the phase modulation. So I could take my envelope and feed it into that amount control, and I get this dynamic control right in the Banshee Reach. Actually, there is one quick thing I want to explain about the difference between FM and phase modulation that's really useful when we're using analog oscillators to do our modulation. As we saw before, if we are using a sine wave to modulate the speed of another sine wave, then what's happening is things are going faster when this part is high and slower when these parts are low. When the modulator is high, it makes the carrier go faster. When the modulator is low, it makes the carrier go slower. And faster means higher in pitch, and slower means lower in pitch. So it's actually really significant for doing FM synthesis that the positive bit and the negative bit are the same size. Because if, for example, there was a thing called a DC offset, where in fact a lot of the waveform is at the top and less of it is at the bottom, then there would be more positive than negative. And this would in fact, even with Thru-Zero, mean that you get a pitch change with your end result. Or if, for example, the positive bit was really wide and the negative bit was really narrow, then you'd get more positive than negative, so you'd be going up in pitch if you modulated a carrier with this. And that doesn't happen with phase modulation. So it's really important in FM analog synthesis that you have a nice symmetrical waveform that is not shifted up or down from the center point, which is called a DC offset. If you're finding that you have Thru-Zero oscillators and you're getting a pitch shift, that could be the reason. Gosh, well done. You got through the thing about FM. So exponential, it's really whacked out and crazy, but it's very hard to tune. Linear, it's tuneful FM, but only to a limited point. If you go beyond it, you might be asking the oscillator to go slower than zero, which it can't do. So you get tuning problems as you ask one oscillator to change the speed of it too much. One way around that, by the way, is tune it up. Tune it up in pitch so it has some room to go a bit lower before it bottoms out at 0 hertz. And then, of course, if you have a Thru-Zero oscillator, then you're allowed to go Thru-Zero and it will bend back and make the correct waveforms, which will keep the pitch the same. And finally, phase modulation is the most tuneful of all. And you can use imbalanced waveforms as your modulators, and the results will always be in tune. Wow, kids, we've done FM. What else can we do with analog oscillators? Oh, mate, there's so many more things, such as ring modulation. What is ring modulation? Well, it's when you take two signals and you combine them with a ring modulator. And what a ring modulator does with those two signals is it's mashing them together and creating two new ones, which are different pitches to the ones that went in. To be specific, you get the pitch that is the addition of the two plus the difference of the two. Really weird, isn't it? It was originally invented as a way of sending both data and voice communications down the same stream of audio, or, well, radio waves. It produces strange, clangorous and inharmonic, quite often, tones that are very different to the two things that go in. It makes for a load of really interesting, weird, whacked out tones. And another really fun thing to do with it is to have one of your sound sources be an audio input, such as a guitar or a voice or something like this. If you ring modulate an oscillator against a voice or a guitar, you get really weird effects. In fact, you also get the Dalek voice, because that's how it was done. So if I was to take another sine wave and another sine wave, I'm going to use the jeweler's cast, which is also a ring modulator. Very cool. I'm going to put one oscillator into input 1 and the other into input 2. Here we can hear the mix of the two. Here we hear the ring modulated version. And so we're getting two signals in here. We're getting the frequency that is both of these added together, and we're getting the frequency which is the difference between them as well. And it's very different to that. Very cool. Very weird. I love looking at the patterns. So that's one oscillator. That's the other. And you can actually see how one is sort of creating the shape of the other, as it were. That to that. Weird, isn't it? We can, of course, try different wave shapes. And we get really interesting spiky wave shapes out. And we may wish to use the vary shape outputs, which let us very quickly blend between different shapes. And the really important thing to stress here is you cannot get these shapes by just mixing the oscillators together. It's a fundamentally new form that is created with a ring modulator. And I think that's kind of why it found its way into a lot of vintage synths, because you were just able to get all these interesting, kind of clangorous, weird metallic tones from just two analog oscillators in combination in what is actually quite a simple circuit. And can we get some sort of, melodic stuff out of it? And yes, you can. And it really matters where you tune things. And the simple answer to this is just to say experimentation is important, to find intervals that work well with each other. And if I was to control the 1 volt per octave of these oscillators at the same time with my key step. Let's get the octave. I like that. I think that little friend needs a cheeky weasel of a filter on it, doesn't it? I don't know why this filter's a cheeky weasel, but sometimes, sometimes they are, mate. That just happens. That happens sometimes. Like this. So we get this other tone. What happens if we use the same envelope and we also sweep the oscillators? Here I'm finding that I can take one of them and sweep it quite hard through the Thru-Zero FM inputs, and it still sounds quite coherent melodically. What if we change the phase modulation? And then what if I swept them both equally? Yeah, it's pretty cool. So if you have a ring modulator, it's not just for inharmonic things. With careful tuning, you can make melodic things. But do bear in mind that the pitches will not relate to the pitches that you have the oscillators set to. So you're going to need to do some trial and error. Next up, AM synthesis. AM stands for Amplitude Modulation. And like the differences, quote unquote, between FM and phase modulation, there's really quite a similarity between ring modulation and amplitude modulation. But they do differ in the end results, is the simplest way of putting it, because I just really, really can't be bothered with maths. And so once again, we can hear a sine wave. And once again, we have another sine wave. An amplitude modulation, all we're doing is we're using one oscillator to vary the volume of another oscillator. But we're going to do it at audio rates. If you used an oscillator to slowly change the volume of another oscillator, then it would really be like tremolo, right? And if I use the jeweler's cast again, it has an amplitude modulation capability. I will feed a sine wave into input 3, and we hear this one on the right. And then I'll take the sine wave of this one, but I'll feed it into the CV mix control. And what that's going to do is move this knob for me, which in effect is changing the volume of the other oscillator. This is just a VCA. A voltage-controlled amplifier changes the volume of something using a voltage, and that voltage is going to be an audio rate sine wave. So what's happening is that this sine wave is controlling the volume of this sine wave at audio rates. And if I turn LFO mode on, you really hear it. Because it's just going on and off, right? That's tremolo, right? And all AM is audio rate tremolo. But we start to get a thing that just sounds a bit kind of FM-y, and it sounds a bit ring modulatory. We kind of do hear the original oscillators. That's that. It's still there, but it's got this other sort of zinginess applied to it from having its volume changed. And just like when we were doing FM, and just like ring modulation, it really matters how you tune this thing. And you might like to tune it melodically, if melodies are your bag. And we find there's just another world of little tones that can be had. Reminder, you're hearing sine waves, but we are seeing something on the scope which absolutely is not a sine wave. And I really enjoy the tones you get from AM. There's a kind of like warm sort of cheekiness to them, for want of a better term. And once again, we may wish to stick that through something to kind of gate it. That is to turn it on and off. And I'm going to stick it through the Centaur's gates. And I'm going to use my mate, the maths. Been my friend since I first got into Eurorack synthesis, this one. And I would be remiss not to just try this. Uh-oh, triple AM. Because I'm using a filter as another AM source here. And interestingly, something I did not do earlier, which I really strongly recommend, is using oscillators to control filters at audio rates. In fact, to do FM effectively. And I could do that here, like this. Because with the right settings, you can create these really like wicked raspy effects. So this is FM and AM in combination. We are FMing a filter. It's such a good thing to do. FM your filters, friends, using analog oscillators. And you've got spare outputs here, like. They should just be put to use. Let's change the octaves these are at. Woo. You can make something that's got a lot of high frequency and low frequency at the same time. Really it's really lovely, really lovely. These like zing sine waves that are possible. Yet another really cool way that you can blend analog oscillators. And all you need are 2 oscillators and a VCA to do it. What's next? Well, it's wave shaping. I don't know if you would technically call this a form of synthesis, but I do, because just as we've been combining oscillators to make entirely new shapes in novel ways, you can use a wave folder or a distortion module to make completely new tones from an oscillator. And I feel that that really is the definition of what we've been doing before. And obviously, as with all these techniques, you can combine them together and see what insanity you can wreak. So we know about our friend, the sine wave, right? We've been using them up to this point. And what if we were to run a sine wave through a wave shaper? So once again, our star of the show is clearly the Jeweler's Cast, which is really, I am genuinely impressed with this module. It's very good and very useful for all kinds of different things. In this instance, we'll take that same sine wave and we'll feed it in to 3. And there's a little switch here that says FLD or DST, and that means distortion or folding. I have it on folding right now. Let's turn that up. Wow, very cool. This creates a very FM-like result. And what it's doing is it is literally taking the waveform and folding it over and folding it over and folding it over like you're folding a piece of paper over and over and over until it becomes a new wiggly shape. And very importantly, hear how it's at the same pitch. It's timbrally different, but it's still playing the same note. So this is a very economical way of turning a simple sine wave into something really interesting without losing pitch or having any of the difficulties that we might have with doing non-Thru-Zero or non-phase modulation, FM, or indeed ring modulation, and some of the other things we've looked at. It makes this wicked, wicked, wicked sound. I love it. And of course, we're folding sine waves. And if we folded different types of waves, such as a triangle, it'd sound different to a sine. Oh, mate. Would sound different to a saw. Now, a square wave, it really struggles. There ain't much to fold with a square wave. So you've got to use things that have curves to them or angles. It's so cool. I love it. And so we're starting to perhaps see that if we modulate the fold amount and if we modulate the waveform, and now I'm using this like vary output on the Banshee Reach, which is super cool. This is one output that smoothly morphs the waveform. And obviously, as you can hear, if we're doing some kind of crazy process to that waveform afterwards, then it really matters what you feed it. And that creates a really interesting timbral change, as much as changing the fold amount itself does. You could do a similar thing without the vary output if you just mixed the outputs of an oscillator together in varying degrees and then ran them through a wave folder. You might want to use a VCA and LFOs or, a sequential switch or something else to do it. But it's just one of the cool things about this setup, just makes it really easy to do that. And there is a CV input for shape, and I will use it. Comme ça. And I might make it negative so that I can make it go back. And then I might use my envelope, who's hanging out feeling lonely, to control the fold amount, right? It's just starting to get into all like manner of coolness here. I just really love it. Now I'm using the LFO that's controlling the Waveshape to also control the fall time of the LFO that's controlling the wavefold amount. We might like to use attenuators to rein in these modulation amounts so they stay within really cool values. So you can play it on a keyboard, no problem, sequence this without kind of detriment or potential like tuning shifts. It's just easy. And I could combine things. Can you imagine what happens if I go sine wave into phase modulation? Wow, that sounds like Skrillex's fever dream. Get well soon, mate. Oh, mate. Yes, mate. Super cool. I'm FMing this oscillator and then I'm wavefolding it. And I'm modulating the Waveshape. Such a good sound. For those of you who are sort of scholars of the world of synthesis, you might be realizing we're starting to get into kind of Buchla structure territory, aren't we? Where you have one oscillator that can frequency or AM modulate the other, and which you can then apply wavefolding in combination with. That's basically what a music easel does. And so even with just these simple things, in the right combination, you get such complex tones, such badassery. So then it's about combining these things. What fun. And finally, additive and subtractive. Why am I lumping these things together? Well, because ironically, we technically do a great deal of additive synthesis when we do subtractive synthesis. No, really. So what is additive? So if we look at a sine wave, we can see that the sine wave on a spectral analyzer is just a big line, a single spike. And the single spike's frequency is whatever we've got the frequency knob set to. 110 hertz in this instance. But if we look at a saw, we may be able to see how we have a spike. So nice to listen to that, just raw by itself. But you have additional spikes going up above. Oh, what is this telling us? So in a sense, the bottom part, known as the fundamental frequency, is kind of the same from sine to saw, but because it's got all these other spikes, that's changing the sound. And since the fundamental of a sine looks just like the fundamental of a saw, and all of the other little columns look the same as well, just shorter, could we make a saw wave out of sine waves? So if I get another sine wave, and then I need more sine waves. And remember, we can make our centaur's gates turn into a sine wave. And so after a few minutes of messing around and tuning, here's the saw wave, and here's my sine wave. 1, 2, 3. Now I've run out of oscillators. And I can see that there are many more little harmonics up here, which I haven't got, and I think I need. I can't make this sound with just 4 sine waves. But it can make quite an interesting sort of organ-like sound. And indeed, like organs, are basically additive synths. And if you have lots and lots and lots more sine waves with the kind of like limitless power that you might find in a computer, then you can absolutely synthesize things from sine waves. And to do it really properly, you'd have each sine wave going through its own VCA with its own envelope. So you could change how the sine waves came in and out over time. There have been synths that could do additive synthesis. Kawai had the K5000, which is a thing of legend. It's really hard to do in modular because it requires such horsepower. You need loads and loads and loads of oscillators. But I still think it's an interesting thing to mess with. If you find yourself in a position to be able to tune lots of oscillators, then you can make quite interesting stacked up organ tones. But now, this whole notion of subtractive, well, it is additive. And so how, pray tell, might subtractive synthesis also be additive? What subtractive synthesis refers to is taking a thing that is rich in harmonics, in the very little spikes that we've been talking about, full of spikes, something like a saw wave, for example. And we take a thing that is full of spikes and we remove spikes with filters. Bright and spiky, and we run it through a filter. And our life is good. We can even see how the spikes get removed. We can also see that resonance adds its own spike. And we could also consider how we might blend together multiple oscillators to make a much more rich sound that we may wish to filter. And what really is adding together two oscillators, if not additive? We're blending multiple harmonics together to make a more complex sound. And we see how a filter can emphasize harmonics with its resonance control. It creates a new spike. It's very cool. And we see how distortion can change. And it can also introduce harmonics too. Or how wave folding moves harmonics around. And if we use the Waveshape outputs of the Banshee Reach, we can also add in sub-octaves. And then we can animate the filters. And then we can push the little button and make the centaur more polite. And then we can run the filters in series with each other. So we have two filters acting on the same signal. One high pass, one low pass. And so we've learned that there are many, many different ways that we can combine together a few basic building blocks. And that we can use these methods in combination with each other. I hope this will encourage you to experiment with things that you have, and obviously links below to these analog modules from Shakmat. Because as we've discovered today, there are many different ways to patch just a few modules. Thanks.